Good evening, and thank you for joining us for this live streamed presentation, all about gravitational waves with Hyun Lim. I am Galen Gisler with the Pajarito Environmental Education Center, or PEEC, located in Los Alamos, New Mexico. I will be the moderator for today's talk. This talk is being recorded. We're able to offer programming at this time because of our wonderful members and donors, and we'll send you an evaluation form after the talk using your comments to improve our future programs. Hyun will be taking questions via Zoom chat. Type your questions for him into the chat window at any time during the show, and I will relay the questions to him at the end of the talk. Hyun Lim got his PhD in physics at BYU and was a postdoctoral researcher and has now converted to staff in CCS2 and the Center for Theoretical Astrophysics at LANL. His research interest is in studying dynamics of compact objects, such as black holes, neutron stars, and white dwarfs, to understand various phenomena in the universe, including gravitational waves, the subject of this talk. At the end, we'll relay the questions to Hyun, but at the moment, I'll turn it over to Hyun and welcome Hyun, and you can start your talk now.
Okay, now I am muted. Okay, good evening, everyone, and thank you for joining today. So I'm Hyun, as Galen said. I'm working at the LANL. So today I am talking about all about the gravitational waves. So there are recent some exciting more newses and some future newses. So my talk will be straightforward. I want to talk about a past, what is the gravitational wave and how we observe it. Then I want to talk about the present, and also, of course, the last one will be a future. So first, talking about the past. So September 14, 2015, LIGO, I will talk about LIGO it is soon, observing gravitational wave from merging two black holes. So when two black holes, they inspiral each other, when they close and they inspiral faster, and they merge and turn to ring downward. And then that create these signals, it's called the gravitational waves. And again, due to COVID, we are doing this show in this Zoom's situation, but this is actually our PEEC planetarium. And then back in the days, we pointed out where the gravitational waves were observing in our sky. So hopefully next year or some later time, we can do this again. So before digging into more newses, and we must talk about what is the gravitational waves. So gravitational is thinking about the wave. So usually we call something called the ripples of the space-time. So you can easily analog what that means by if you throw some pebbles into the pond, and then you will see that this whirlpool from the where pebble down. So this is exactly what gravitational wave is doing. We have some events such as black hole merging to black holes, and that makes the ripples in our space-time itself. So what that means is, so due to that energetic event, our space-time is squeezed and stretched itself, and then that's what we are seeing using the observatory. So what that means that any object, any massive object that's spinning or moving, that make the gravitational waves. So even this spinning like a cute animal also create the gravitational wave. If you somehow rotating yourself, you also create the gravitational wave. If you see something moving each other on the street, that also create the gravitational wave. So then why this is so hard to measure it and why this is so exciting event, what we are talking about. So then we first need to question ourselves then how much stretching, squeezing our space-time itself. Don't need to worry too much about the actual formula. I really not a big fan to put the formula, but this is one of the easiest way. So the H thing is called the wave strain. That's the fractional stretching compressing of the material. And then this guy is the a measure of how much accelerate and how fast about it. And that's the distance from the sources. So like, even without this formulae, if you see that this like a 10 to the negative 44 number, like this, which is incredibly small, like billion is about 10 to the 9, trillion 10 to the 12. So this is like 1/trillion times, trillion times, trillion times, billion, something like that. So it's like really small number. Even the Einstein, who are invented theory of general relativity and expect gravitational waves, he said 10 to the negative 44, this is too small, we'll never see this. And I'm not made this story. This is actual his paper written in German. And if you translate it in English, in any case, one can think of the A is still like this value, the equation 21, will have a practical vanishing value. So he thinks that no, we're not gonna see that. So then people thinking about that these some more extreme cases, what if we have some two black holes that orbit each other and merge it? So people do that computation, again, the H, the value, we want to measure it. And they some, yeah, black hole has the mass of the sun, and distance is like a millions of the light years, and they do some like some computation, and they got a number 10 to the negative 21, so which is much better than 10 to the negative 44. But this is, again, still small. This is like 1/trillion times billion. So if all of you like me, then say, no, it's still too small, it's not gonna see that. But of course, there are three great scientists like Draper, Kip Thorne, Rainer Weiss. They think that the 10 to the negative 21, maybe we can do this. So they started thinking about that, how we can observe this small squeeze and stretching when the two black holes are merging each other. So they started a project called the LIGO Interferometer Gravitational Observatory. Now we call the LIGO. So first construction happened like mid 1990 in both Hanford, Washington and Livingston, Louisiana. And then after their construction, they do their first operation run, about 8 years. And unfortunately, there's nothing really exciting event happen. And they think that maybe we need to upgrade it, that LIGO, to have more sensitivity and cover like a larger space. Then they shut down and started what now we call the advanced LIGO. So what we for LIGO these days is actually advanced LIGO. And advanced LIGO started to operate on 2015. And surprisingly, as I said, the first gravitational observation happened September 14. So even they do their testing run and they detect the gravitational waves. So like that's some example picture how it look like. We have this like really long arm vacuum chamber, and people work on it. And at the end, we have this like a meter type of it. And this is like a really big chamber. You see the people by the sides. And then of course, there are way more technologies happen, even not just one of the people can understand all about it. So this is how it looked like inside of LIGO. So then how LIGO detect the gravitational wave. So this is just some example schematic picture. So that's the laser, and that's at the end of the L-shaped 4 km arm. So what they're doing. So they shoot the laser into the splitter, and splitter travel into that 4 km. So at the end, they reflect it through the mirror. And during that reflection, and there will be some phase difference. So if really nothing happened, that phase difference should be the same. But gravitational wave, as I said in previously, they squeeze and stretch space-time itself, means that mirror also squeeze and stretching out. So that makes this phase difference, and that's the what we are measuring about the gravitational wave. And yeah, so in such an event, like two black holes merging each other, which is like what really energetic event, and you see that some ripples are getting stronger, and they merge and they emitted that gravitational wave, travel through whole space-time in the universe. and that reach the Earth. Yeah, of course, this is still a really exaggerated scale, but this is still like what happened when you see that this gravitational wave. As I said, the value is really small. So like what we really detected. So this is like a zoom into the hydrogen atom, which to the center. And then the change of the distance is like the thousandth of the diameter of the proton. So like this is remarkably like a small changes. That's what we are detecting due to squeezing and stretch of the our space-time itself due to the gravitational wave. And as I say, gravitational waves, but this is not really sound. Maybe I need to do it. I hope that you can hear some transforming sound. You hear that some like whoop whoop, some plopping sounds. Like the first one is like some sound turning to the frequency, turning to the sound, and last one is like slightly increasing to hear that plop sound is better. Yeah. So this is still like sometimes people say, yeah, that's the harmony when black holes are merging each other. And of course, for this contribution, like 4 years ago, 2017 Nobel Prize in Physics was awarded to these three scientists, Rainer Weiss, Barry Barish, and Kip Thorne. And unfortunately, one of the original developer, Ron Draper, he passed away like year before the Nobel Prize is awarded. So, and the Barry Barish has also big contribution that they awarded these gravitational waves. And from 2015, people start to observe gravitational waves. So that's the really first black hole event from what we call the first observation run. It's about just, as you can see, 2. And then now people also performing more run. It's called the observational 2 run. Then we have this 9 event detecting from the LIGO collaboration. And now we are having observational 3rd phase. This is actually happened from 2019 through 2020, but people are still working on that analysis. So first half was released last year in what we call the observation 3 run A, so called as O3A, has the 39 events. And then recently they're releasing, I will point it out later, 2 more events from the last half of it. So now we are having total 52 gravitational wave from the merging 2 black holes and merging neutron stars, and finally merging black hole and neutron star. I will get into these details. So this is the history about a gravitational detection of the gravitational wave and LIGO. So now we talk on the present. So I want to emphasize the 3rd LIGO observational run, which is the period of the November 1st, 2019. Original plan was April 20th, 2020, but they terminated earlier, March 27th, due to COVID. So COVID actually impact way widely larger than what people thought. And during this about slightly less than year and a half learn, we have like a 1,200 alerts. So during the 3rd observation run, even you can see that this public alerts. So like when they think that there might be a gravitational waves and they start to analyze it, and they down that 1,200 into the 56 candidates. And they also released the catalog called the GWTC 2.1 that also contains first 2 observation run. So GWTC stands for the gravitational wave transient catalog. So that contains all the information about what's the masses of before they emerge, what's the mass of after they emerge, what's the distance, signal power, etc., etc. And then they release O3A, the half of it, the first April, the first half of it, November 1st through the October 1st, 2020. And then they will plan to release O3b data soon. So as I said, there are 56 candidate and 52 confirmed gravitational wave. I'm not gonna say everything about by detail, but there are some like kind of the exceptional discoveries about the O3A. So first one is called the GW190412. So how you can read this, like GW of course stands for the gravitational wave, and first two letters the year, so 2019, and around two letters is the month, April, and of course 12. And this is their first black hole collision. That's the two black hole mass has had widely mismatched mass. So the small black hole has about the 8.4 masses of the sun, and then the another one has about the 30 times masses of the sun, technically 29.7 masses of the sun. This unique property about this gravitational wave allow for the observation of the fundamental property of the gravitational wave. So starting with some pioneering work, Einstein, and later define some different physicists, Newman, Penrose as a winner of the 2020 Nobel Prize, and Thorne, and many others. And gravitational radiation from the compact binary was shown to be predominantly quadrupolar. This quadrupolar radiation can be thought of like some main sound that is heard when plucking the string on a guitar. And however, like a musical instrument, gravitational radiation is predicted to also ring at higher overtone. These higher harmonics or higher multiple are exceptionally difficult to parse out of the signal when the black holes are near equal mass. So these asymmetric masses allow for this subtle signal to be better heard or say observing in the gravitational wave emission. And we find that the data support the hypothesis by factor of the greater than 10,000 versus 1, that there are higher harmonic in this signal. So in the future, the relative intensity of higher multiples may help to better disentangle the properties of the coalescence of the black holes. So this is like exciting to see that how we can map out that the different black hole masses about it. So another interesting discovery is called the GW190425. This is the second gravitational wave event from merging two neutron stars, following from the GW170817. And then unlike black holes, when two neutron stars merging, and of course neutron stars composed with the neutrons, then when they merge, they emit the gravitational wave, but they also emit the gigantic amount of the material through super fast, high temperature that glue out to the space. So what that means that when two neutron stars are merging, there are multiple different observational properties we can do with it. So first, when they merge it, LIGO, they observing the gravitational wave. And they also emit the, something called the gamma ray. So the Fermi integral project observe the gamma ray. Then they go to the X-ray, and they go to this radio, and also optical length radio, and also radio wave. So literally, so this is the plot from that first neutron star merger event GW170817, and our human being using all the possible techniques to observe some object in the universe. So this is what we call the now multi-messenger astronomy. So from the gravitational observing event, and also following satellite missions, and also several radio telescope that also can see that electromagnetic counterpart in terms of the different frequencies. Another interesting aspect about neutron stars, these are that the production of the heavier element of the universe. So we are thinking that when universe is created through Big Bang, and of course that's a super energetic event, and then hydrogen turn it to the helium, lithium, following the older period table up to argon. Argon is really stable element, so without any strong, say, engine to produce further than argon, it is like almost impossible to generate this heavy element in the universe naturally or say automatically. So there must be some engine to create it. And neutron star is like the one of the main source to create the heavy element universe. And of course, we know that there are heavy elements in the universe. And that's what we are called the mass fraction plot from the nucleosynthesis. And this is the mass number. This actually identified the element. And this is the some nucleosynthesis plot. And that's the plot of the solar abundance. And you see that these peaks actually matched with the what solar abundance has it. And about near the 191, like about here, that match the peak, and that's the gold. So that's the reason some people also called neutron star merger are the golden binary, because they're a main source to create the gold, what we are seeing these days. Like maybe some people's ring, even some people's teeth, or computers, etc., etc. So that's the neutron stars tells us like not only having a lot of the optical event or electromagnetic event in the universe, but also they also explain that the existence of the heavier element in the universe. Okay, so another one is called the GW the 190521. That's the binary black hole with total mass over 150 times the mass of the sun. So that's the some different plot people make it. So you see that the GW 170608, and if you compare it with this event, that has vastly larger mass than this, and also that's the like previous the asymmetric masses. You like compare this black hole versus this is way larger. Again, then why this is interesting? So now I'm mentioning that the like different masses of the black hole. Mass is the one parameter to categorize the black hole. So some mass, that's the plot of the mass of the sun. And there are some primordial black hole. People think that theoretically, at the beginning of the universe, there are really, really, really tiny black holes created, about the 10 to the negative 20, 30, 40 mass of the sun. But there are some like stellar mass black hole, about the 10 times mass of the sun, or 20 times mass of the sun, etc. And there are another category called the supermassive black hole. It's like a million, like even billion times mass of the sun. They usually existing in the center of the galaxy. So we know that. We know that this exists of stellar mass black hole from the X-rays and also gravitational waves. And also we also know that there's existence of the supermassive black holes. But the question is, then do we know this black hole mass about 100 to the like less than like a million in what we are called the intermediate mass black hole? And for now, they are not really confirmed yet. So we know that the existence of the supermassive black hole by observing the Sagittarius A galaxy. This is about 26,000 light year away and has the 4 million times mass of the sun. And people tracking that the how star moves center of the galaxy. This is the starting from the 1995 and up to 2019 data. And people see that this trajectory and calculate it, and they confirm that yes, this is actually the really big massive object is called a supermassive black hole. And not only that, you may hear about that some exciting event called the Event Horizon Telescope. People do some kind of different telescopes among all the Earths and using like that the camera to take the picture of the black hole. And sometimes like we just see that this blob, or some people say Sauron's eye from the Lord of the Ring, but this is like a huge object. So this blob is some like these can just that black holes emitted, and the center area is the black hole area. How big it is this is your sun, and this is the Pluto, and this the Voyager 1 is currently the path through the Pluto. So you see that like how big supermassive black hole it is. And of course, that's another exciting observation. So to Reinhard Genzel and Andrea Ghez, they awarded Nobel Prize in Physics last year about this discovery about the gravitational waves. But as we return to why this is exciting event, because this might tell us that the intermediate mass black hole exists or not. And also another big question we want to answer is like how this supermassive black hole forms. Like this, like too large compared with the usual stellar mass black hole. They have 1 million, 10 million, even billions of them. So we hope that maybe more data can explain some population of the black hole and also their binary formation channel. And maybe we can find some kind of intermediate mass black hole test, maybe 100 or thousands mass of the sun, and lead to some understanding of black hole formation too. And another interesting discovery is O3A, is called the GW190814. So that's the first collision that involved the object in the mass gap. I'll explain what that means later, between neutron star and black hole with the wide mass difference. So mass gap, the question becomes that how black hole is formed. And we have different theories. And then in that certain area, like easy to think that if you squeeze some massive object into certain smaller radius, nowadays what we are called the Schwarzschild radius, that turn into black hole. Like if you concentrate a mass into really small, tiny radius, that turn into the black hole, theoretically. And then of course, in real life, we have like rotation and different stuffs. It is really hard to see what mass of the say star at the end that turn into the black hole or not. So even when two neutrons start merging, the previous GW17117 event, they can turn into what some people call the hypermassive black hole. Then question became that is that massive, hypermassive neutron star is stable, not turning into the black hole, or they just collapse themselves into turning into the black hole. So there are some mass area, it's called the mass gap. So, and people really don't know this should be a neutron star or black hole. And also the mass difference is pretty big. So that's a really good opportunity to see what kind of the mass distribution we would see about this mass gap range area. Then we can somehow identify using theoretical model to know this should be a neutron star or this shouldn't be a neutron star, or say this should be a black hole to see it. So we hope that in the more future detection, we may want to learn more this thing about it. Yep. And also I didn't mention more thing in the O3A, but I think that this is about a good time to move in O3B because we only have 2 more data, but this is like a really interesting. Like I didn't mention it, and they are also finding from O3A a possible smallest black hole merger, which gives some more concretize our mass map of the black holes about it. But what I told so far, we observed gravitational wave merging 2 black holes or 2 neutron stars. But now natural question became that what about the black hole and neutron star merger pair? And surprisingly, during analysis of this O3B data, we have found 2, GW20-0105 and also GW20-0115, like 10 days after each, we find the gravitational wave from the binary neutron star merger. Black hole, neutron star merger, not binary neutron star merger, sorry. So you see that there we have 48 black hole merger and 2 neutron star merger, and also this black hole neutron star merger. And how it looked like, so this is just some artistic representation of the computer simulation. You see these black holes, and then when neutrons start reach them, and they eject some material, it's what we call the tidal disruption event, and they merge it, and then they omitting a lot of the material too. So again, then why this is important and interesting, like these 2 systems are important because they are like first clear discovery of the neutron star black hole binary, which is the type of the source that had never been observed with either electromagnetic signal. As I said, once neutron star merged, they omitted a bunch of materials. So it could be observed through electromagnetically. But we never observed electromagnetic sense and of course, gravitational waves. So what it tells us that this system do exist, but this is more rare than binary neutron star. So unfortunately, we only have these 2 data points. So the people like estimating what's the numbers, what we see black hole neutron star merger is still uncertain, but we have estimation that about 10 neutron star binary, there will be some one neutron star black hole binaries. And then why this another part of the interesting about this that the then we can question becomes that the like what this system will be because we want to also model the system with the different physical parameter of this binary system, as well as different theories, like for example, like how violent is the supernova explosion that leaves behind neutron stars and black hole. Is it so powerful that it can be destroy the binary system altogether, etc. So with having access to this neutron star black hole merger system that will define these models, and our understanding of the formation of the evolution of the compact object will be better. So what we are doing with this gravitational wave data, and of course there are a bunch of things we can do, and of course physicists doesn't believe anything in general, so even we want to test general relativity. So you see that the whole different acronym like this test performed, like don't need to worry about it too much, like they find what's the residual after subtracting best fitting waveform, low frequency, high frequency in spiral, parameterized deviation from waveform. I also meant quadrupolar radiation form, changes if the gravitational wave propagate, and the ring down phase, and higher order gravitational waves, polarization, echoes, etc., etc. And that's the all different source of the gravitational wave. You see that number, and if you see the underscore with this number, and sometimes we observe gravitational wave in same dates, right? So and then people put the time in UTC, hour, minute, second. And then people confirm comprehensive tests with all different tests. So far, we find no evidence for deviation from general relativity on account for physics or evidence of the systematic in this analysis. So Einstein triumphed, he's right in this field vision. And interestingly, general relativity is not complete. It is not mingled with the quantum mechanics, and people, of course, want to overcome the general relativity. So people made a bunch of different theory that beyond general relativity, so like quantum theories of gravity, higher dimensional theory, etc., etc., etc. Now we entering the gravitational wave observation. So what that means that this is the example of the computer simulation, like merging two black holes, and then this is the example of the gravitational wave waveform with adding some hypothetical particle called the axion, and then this is the different weight of the axion. And you clearly see that when this number is changing, and also the wave form is changing. And of course, everything is the same except this, like they have masses of the black hole simulation are the same, the initial distance are the same. So people hope that once we have enough more data, then we may detect some deviate from the general relativity that confirms that the beyond general relativity theory, which will be exciting event for the future. And not only that, gravitational wave actually help to define new particles. You may hear about that the Large Hadron Collider in Switzerland called LHC. They tested it and they found what we are called a Higgs particle, which gives the mass of the particles. And that's the somewhat traditional way to understanding the particles. Like they shoot the small particle really, really fast. It's about 99.99999 speed of light. And when they collide it, and of course they break it and they track this trajectory to see the a charge and masses, like how it looked like. And indeed, gravitational wave help to identify signals from the new particles. So this is still like a black hole, and then put some kind of again hypothetical some particle cloud, and then when black hole spinning rapidly, and then they also emit the gravitational wave due to these interactions. So this is still about some kind of mass of the particle and some detectability, and you see that there's different names of the parameters, and also observatory system. So people hope that this could be helped to also identify different particles through these gravitational waves. So this is actually people's ongoing work. So we are not only observing gravitational wave from different sources, black holes, neutron stars, black hole and neutron stars. And using this data, we identify the physics theory, even finding a new physics from this data. So now we are talking about a future, about the plan. So this talk, I emphasize mostly about LIGO observation third run, which is having early termination due to COVID. And then originally people released some date for the observation for run about September 15th. And due to many different regions, include COVID, actually we will announce something by November 15th, some more concrete plan about it. And then I just say the LIGO, and of course LIGO has the big collaboration, and then they join into the different gravitational observatory. The Borgo is located in Italy, and then Kagra is located in Japan. They actually joined 2019 December during the O3 run. And then we are building the additional LIGO in India and hopefully joining sometime 2025. And then not just running these gravitational waves, but this is about like imagine about the space range that LIGO can cover. That's the initial LIGO, the LIGO built in 1994 and 5 and run in 2002 to 2010. And of course, we didn't detect anything, so we increased our detection lane. Now what we are called the advanced LIGO. So it's about the 10 times larger radius. Again, we are thinking about a volume. So if you increase your radius by a factor of 10, then your detection volume increased by a factor of 1,000. And this is not done. People is expanding more. So like this is about 1 billion light year range. And then this is the O3. It's about 50% better than advanced LIGO. The O4 is about twice larger than advanced LIGO, which is we have 8 times larger volume to detect the space. And O5 is about 6 times larger than advanced LIGO. So like what that means that we have about 120 times larger than advanced LIGO about this detection area. So hope once we reach to that point and then LIGO India will join, means that we will cover more sky. And by expectation, we will detect gravitational wave every single day. That's the expected value. So which is about what? About 10,000 times larger than initial LIGO detection rates. And of course, this is not done. I'm saying gravitational waves, so we can simply identify wave as the different of the frequencies. So this is about that the first gravitational wave detection event frequency range. And as you can see, there are way more different sources we can thinking about it. The compact binary inspiral, core collapse supernovae, pulsars, a compact binary inspiral. That what that means that we have black holes, neutron stars. So now we identify everybody, black hole mergers, 2 black hole mergers, 2 neutron star mergers, and black hole neutron star merger, which is great. And there will be more things. We have massive binaries, like millions of the galaxies, supermassive black holes, so technically galaxies can merging together, and supermassive binary, some stochastic backgrounds, some different galactic barony, extreme mass ratio in spiral, which means that the mass difference between 2 objects is more than 1 million or so. Some merger from the white dwarf. So which means that the LIGO is not the only one to cover it, and people have a lot of different plans to detect all these gravitational waves, like for example, this large array to have a stochastic data, and this LISA, ELISA, this LIGO. This is actually satellite mission. Now, what I call this space-based gravitational wave observation. So we shoot the satellite to the Earth orbit, and then we'll follow the Earth, and this is done, and this triangular, and what it looked like. And of course, gravitational wave squeeze and space-time itself, that means that the squeeze and stretching everything, not just Earth. And then of course, gravitational waves can be observed through the space. So that's the plan to be launched about 2035. It's called the LISA mission, Laser Interferometer Space Antenna mission, led by European Space Agency and also NASA. So we are pretty excited to some observed different gravitational wave from the different sources. And actually, if you're interested in it, you can also help them, because we are, even the O3, there are about 1,200 outlets happen, which means we have a lot of the computational power required to identify which one is correct one, which one is not correct one. So this Einstein at home and also Gravity Spy, this is about the idea about cloud computing to see, help they identify the gravitational waves. If you go to this website, you can download it. When you turn on, they will use like some amount of the resource of your computer to identify identify the possible sources, and Gravity Spy to some signal called a glitch to again identify gravitational waves are better. And of course, you don't have to do it, but it could be a cool project. Okay, so this is all about it. What I want to say. So now. So I want to say, so we can now see, and of course, as you listened previously, listen to the universe with the new eyes and of course new ears. And as I mentioned it before, like gravitational waves offer like a new insight into many fascinating astrophysical phenomena, not just compact binary mergers. It tests the theories of the general relativity in physics. It finds new particles through the gravitational waves. So we hope that a lot of the mysteries will soon be unraveled. And of course, there are a lot of the unknowns. So thanks. Any questions?
Thank you, Hyun, for a very entertaining talk on gravitational waves from lots of different types of sources. We do have a couple of questions in the chat. One question is, do gravitational waves propagate at a uniform rate, and what is the speed?
So gravitational wave propagate at speed of light, and then which is the good thing about that the gravitational wave does not interfere, easy to say, with matter. So once they shoot it, it travels speed of light. It passes whole of the universe. So I didn't show that the plot about that what's the distance about the object, and closest event about the GW170817. This is about 100 million light year, but longest or say farthest event is about 7 billion light year. So which is pretty uniform and speed of light distance. This is that's the reason like why this actually can unraveling a lot of the information about it.
Okay, thank you. Gravitational waves travel at the speed of light, just like electromagnetic radiation.
Mm-hmm.
Another question, how many mergers between a black hole and a star, an ordinary star, I suppose, have been observed?
0, unfortunately. Not really. I mean, so like what people are called for gravitational wave 0, so we never observed, again, we don't have the ability. So I'm saying black hole, neutron star, and neutrons, binary neutrons are neutron stars, right? And of course, we can think that what about the white dwarf and white dwarf? What about the red giant and red giant? Something like that. As I show into some previous plot about the different frequency range, and LIGO, that's the LIGO detectability. So by gravitational waves, none. So we didn't observe any black hole with ordinary stars merging together. But what we sometimes call the X-ray emission or binary, that actually emitting the X-ray when some tidal discharge event happened to the star. And then the question, another natural question can arise is that then why it is so hard to see black holes and other star binary. And that's actually the question people are looking on it. So even I'm thinking about that, why binary black hole is formed. So a lot of the people are studying on what we are called the formation channel. This is still open. There are a lot of open questions. So, but based on the understanding of forming these two, say, massive object into the binary form, usually that's at the end of the star event or captured by or swing by black holes. because black holes are so much big gravity compared with the other stars. So that's the sum of the why black hole binary or some binary that include black hole more common than some other binary system too, in terms of the observing gravitational wave, of course.
Okay, so the answer is that you don't observe them with gravitational waves, but you can observe them through X-rays or other.
Signals, yeah.
Right. Mm-hmm. Yeah. Okay, this is a complicated one from Francis Meyer. Got here late and need to leave early. Swidzinski and Hilburn propose a 4-vector, not tensor theory to replace general relativity, and has predictions that are consistent with GR predictions, except for the polarization of gravitational waves. Understand that this requires determination of the direction of the merger. A while ago, the only merger for which direction had been determined was GW 170817. The analysis of that event is controversial. Any new information?
Yeah, so I'm not really expert on the Swidzinski-Hilburn theory, but if I make the analogy with the different theory, so I didn't specify, at the very beginning, I showed that what we are called the H value strain. So that's what we are actually computed to observe it. And then in GR, the theory of general relativity, they have like what we are called a plus polarization and also cross X polarization. So we have the H plus and HX. So we can somewhat compute what it should be look like by theory of general relativity because of in theory, what we are called something termed called degree of freedom, which means how much freedom the theory allows. And of course, when we introduce some different stuffs, there will be some additional degree of freedom, which means that we have different polarizations too. So there are some theory called the massive gravity. As I said, gravitational wave speed at the propagated speed of light, and none of them, non-massive object can be a speed of light. So if you think that the gravitational wave like a particle, which we call the graviton, has no mass, but massive gravity proposed that what if graviton has the mass? And due to that, there are some additional polarization. So people actually looking at the like the different types of the polarization that maybe violated Einstein's theory of general relativity. And then the digital, the 170817, unfortunately, someone scooped out a lot of the theories. But again, it is not complete yet. So if any new information about beyond GR theories, not really. And currently people focusing is more like testing GR, like what portion or say what sector we need to look more if there are some like a big deviation from Einstein's theory of general relativity. So like some more conservative observational person says, no, having beyond GR theory is more like that be a mathematical, say, playground. But some, like more progressive theorists say, no, Einstein theory of general relativity is not complete. There must be, complete theory that includes GR. So we must find something. So this is still ongoing. So that's the reason that the Y0405 will be exciting. Means we will have way more data. Means we can test way more than right now.
Thanks, and I hope that will answer Francis's question. If not, you can come back with more, or maybe you know her and you can talk with her directly. Mm-hmm. Another question is, I read a story a while back about using pulsars to detect gravitational waves. Has there been any progress in that area?
So pulsar timing array, they try to detect the gravitational wave. So I mean, only thing I can say, there are some like the low frequency gravitational wave maybe hit it like by a hint, but usually, so what we are saying about the signal to noise ratio, or say, let's say easy to say like confidence about a data, and not yet really satisfying gravitational wave information from pulsar yet, unfortunately. So people are still looking on it. So that's the reason that there are so many different frequency bands and trying to find the gravitational wave from the different sources.
Yeah, I understand there's the pulsar timing array. There's a component of that here in New Mexico using the VLA and perhaps some other instruments. So so I guess they're working on it, but haven't gotten any data yet.
Like a really confirmed data.
Right. Yeah. But this is all very exciting, Hyun. The number of detections with LIGO and Virgo and now CAGRA have increased so dramatically since 2015, and in the runs yet to come, 04 and 05, they will these numbers will increase, as you illustrated with the volume of space that's going to be accessed with all of this. That we should have huge more numbers of binary black hole mergers, of neutron star black hole mergers, and neutron star mergers. So we should really start to get some detailed understanding of how this all works, and maybe there will be some modifications that have to be made to GR. What do you think?
Yeah, I mean, that's the hope. Like, one of the paper I wrote is like, yeah, here's this like actually the gravitational wave plot I showed in this talk is actually my work. So hope that there's some like enough data to compare with it. And I know my friends working on the like particle physics field and also astrophysics field. Try to see some more events on it. And personally, I also believe that in terms of the physics theoretical point of view, the general relativity is not really complete. So there must be some theory that overcomes some issue from GR. And yeah, we'll see which one will be a winner.
Right, yes. Another question, what can be said about the observations of about 40 lines of polarized light in the accretion ring of M87?
The M87, the line of what?
That was the Event Horizon Telescope image of the black hole shadow, and yeah.
So yeah, it may be good to introduce, like, actually even at the lab there are the actual experts on the part of this Event Horizon Telescope team. I maybe convince them to giving us some interesting planetarium show about Event Horizon Telescopes. So what I can tell about this image, this M87 image. So this is still like actually like a 2D projection about it. So like this one is still some accretion disk around the like a black hole about it, and this is still some like distortions happen back of it. So this is still like how people's idea about it. Yeah, let's picture about a black hole, and then the way to do it is pretty remarkable. It's like of course naively say once you have a larger telescope, you will have better resolution, which is obvious. So which means that theoretically, if you have some telescope size of sun, then you will be way better image about it. And that's practically impossible. So people connect different radio telescope in the world, and they make the Earth like a whole big telescope to capture the image. And really is like one of them. And they like modified it, and how they confirm this is the actual black hole and all the stuffs, and that part like theoretical and computational effort commit, and people perform like the fluid with their general relativity simulation to see how this accretion disk is moving about it, which is another interesting question, and ask that what's the accretion disk rate, and then also the supermassive black hole shoot something called the jets, and then yet the understanding of this formation of the accretion disk is somewhat better than formation of the jet, but again that's the open questions. So if you have some school children who are interested in working in this field, I'm highly recommending working right now and do some groundbreaking work, then maybe he or she could be a Nobel Prize winner in the future.
That's absolutely right. And the Event Horizon Telescope recently looked at the jet in Centaurus A, and the combination of the Event Horizon Telescope and gravitational waves will probably give us some new insight into all of these processes, accretion disks, jet formation, black holes themselves. It's a very exciting time to to be starting out in science, and I envy youngsters that will be coming up now and just starting to investigate these fields.
Yeah, so like this is really new field, right? Even the first observation is like about 6 years ago. Like thinking about that, some physics theory we learned at the school, like from the Newton about like what 300, 400 years old. Even Einstein theory of general relativity even older than 100 years. And there are a lot open questions. Open it. I explained this some bit, and of course I'm not the expert on every single aspect. So it is really nice time to working on this astrophysics and gravitational physics area.
Yes, indeed. Let's see. Are there any other questions? I've read through all of the ones that have appeared in the chat, but if anybody has any others, please type them in. Maybe not. So remind us when the next observing run of 04, I guess it is. When is that supposed to start?
So the concrete ties plan will be announced November 15th. So we already delayed it 2 months more. I really can't tell like detailed date, but if I say some rumor is like that the early next year will be a target timing to actual start of 04. Yeah, like literally COVID impacts a lot because all the on-site activity is not permitted. So they need to be somewhat fixed, a lot more than they expected, because more than 6 months, they literally cannot do some like the collective activity at the LIGO facility, because there will be like hundreds of people should be in here. And of course, due to COVID, which is now allowed. And when they can do some activity, and then they realize that, yeah, there are way more issues than we thought. So that's the reason like we delayed it more. This is unfortunate. Yeah.
Right. Yeah. It's not as simple matter of turning a switch and then you're running.
Yeah, exactly. Yeah. I didn't
right,
mention all the detail, but if you see how remarkable detailed techniques LIGO has it, this is amazing. Yeah. It
is a very impressive technology that has been developed to the detection of gravitational waves. I had the opportunity to visit the LIGO facility at Hanford in Washington, and it's just amazing. And I'm sure the one in Livingston, Louisiana, and the one in Italy, and the one in Japan. I mean, they all have to work together, and they all have to turn on at about the same time. I mean, there must be hundreds of people involved at each of those sites to get it all in order and working. Yeah, I mean, we're of course impatient to see the results from the next runs, but we just have to wait.
Yeah. So, and then if someone asks that why like other like this observatory matter, what we are called the sky localization. So at the beginning of the picture I showed using the peak planetarium dome, you see that there's some deviation about it. So this uncertain happened due to that we are looking the sky in certain area, and of course there's some uncertainty happen. So like LIGO cannot cover whole sky as you expected. So if you put the different location on it, which means that we can actually cover the whole sky. One of the gravitational events when Virgo joined, LIGO observed it, but Virgo wasn't observed, which means that there are some really local area that only LIGO can see. Now Kagra joined, we cover more sky. And now LIGO India joined, and technically this will cover whole sky from this Earth's point of view.
Right, the more detectors, the better localization you can get, and that's very, very important.